share button on the bottom. All right, hopefully everybody on the online Zoom meeting can see the presentation. Any way to make the All right, folks, hopefully the presentation gods are going to be kind to us. I appreciate, got a lot of familiar faces in the room here, so thank you for those of you who were able to show up and attend in person. For the folks online, I know I have a lot of my reviewers attending remotely, so thank you for joining, and for those of you who weren't able to join in person, thank you for joining us online. Today we're going to be talking about some of my research. This is actually a part 3 to a series I've been giving around containerization forensics. We also did some work around reverse engineering. This particular topic, we're going to end up covering digital forensics as it relates to Kubernetes. And for those of you who are looking at my slide going, it doesn't say Kubernetes. K8, the number 8, actually represents the letters between the beginning of the word and the letter S. So anyways, so you ever see this, now you know what it is. Next slide. All right, yeah, again, anything you see here, you know, this is all based on publicly available information. It's not reflective of anything specifically at you know, my place of business or employment. And of course, it is reflective of some private research that I've done, and so hopefully you'll enjoy that part of it. Next slide. A little bit about me. Look, here's the bottom line. I'm creeping up on about 20 years serving in my profession. I've done a lot of talks, mostly here to this community. That's where my heart is. And just kind of beyond that, you know, I've always been just very spirited about staying on top of my education and personal learning. And that's really what's on this slide. You can go ahead and go to the next slide. All right, let's get into some of the fun for this one. All right, so we're going to go over what's the difference between containers and virtual machines. I think that still kind of trips us up a little bit. We're also going to take a look at, you know, what does a Kubernetes environment look like, and just talk about what the major components are. So as we tackle the main topic of Kubernetes forensics, right, we'll have a better handle on why it is we might be looking at what the thing is on the screen. We're also going to talk about what container orchestration is, because that's really what Kubernetes is doing for us. And then building on that, we'll talk about some of the deployment options. That'll be really brief, guys. There's so many ways. And then also get a little bit into you know, some of the security components of Kubernetes. Again, it'll be security light. You'll have plenty to follow up on if you're interested in that. And then finally, what are those new layers of forensic analysis, right? I said this is a part 3. So again, part 1, we covered a lot from containerization, what our forensic opportunities were. You know, part 2, we dealt with, well, what if somebody decides to bundle bad code with it, what our opportunities were. Well, here we're introducing Kubernetes, so what does that look like? And then finally, from an incident response perspective, right, we're going to tackle kind of what the world sees as the major risk events that might occur with the use of Kubernetes, and then talk about maybe some of the steps you might take if you did experience an incident in your environment, so you can act on those forensic artifacts we're going to be talking about today. Next slide. All right, so here it is. You know, we have up on the screen, you know, again, virtualization, containerization. The virtualization's on the left. Look, really what I like to say here is that, you know, we can talk about this metaphorically. When we think in terms of, you know, virtualization, typically the way virtualization works is that we have a host, and that host has so much memory, it has so much processing, it has so much storage. And when we virtualize, when we introduce the hypervisor, really what we're doing is we're cutting up that hardware almost like a pizza, right? And so when you pick up the slice is gone, okay? When we think in terms of containerization, really what we get into is we start treating hardware more like it's a bowl of soup, right? And let's say you're going to share that bowl of soup with your friends. By the way, it sounds gross to me now I'm saying it out loud, but this is what we're going to work with today. But let's say you're going to share spoons with your friends. Now everybody can get as much from the soup as they like. that's how containerization is different. Now, in practice, what we end up seeing with containerization is that containerization, we actually end up using just the bare minimum libraries, if you're doing best practices, the bare minimum libraries we need to run our application, right? And all that talk between the application and those libraries are actually handled by whatever the runtime environment is that's providing that containerization service. And so when we spoke last, during really the part one of all this, we specifically hit on Docker. And so we'll see more about Docker. And for those of you who didn't know, that's a Docker whale up on the screen. Next slide. All right, so here we go. This is a Kubernetes environment. And at first, it seems dangerously complicated, I imagine, if you hadn't seen this before. But really, there's some important segmentation here. Just to kind of point, you can see if you're looking at my slide on the furthest left side, you can see that furthest left side of the slide, you can see that it's labeled, and we have something called the control pane. And then adjacent to the control pane, we have something, now it's not labeled this way, presentation fail, but this is actually the data plane, okay? And what we're going to focus on right this second is the control pane. Control pane is also known as the master node. Whenever I reference a node, really what I mean is the server or the hardware that's hosting these running components that you see on the slide. And when it comes to the master node's business is this actual idea of orchestration. And so all the components that are running on that particular server, their sole purpose is to manage all these containers we might be running inside our enterprise environment. Just kind of going through some of the pieces, parts. First off, we see a pleasant little green screen kind of to the bottom left of the slide, and that's meant to show maybe an administrator interacting with this master node. And then the components they're interacting with, you can see the arrow goes straight to the API server. The reason why that arrow is so important is that when it comes to interacting with the master node and interacting really with the control pane, all communications go through the API server, okay? From the API server, there's a lot of other communications going on underneath the sheets. One of those communications that's very important is something called etcd. What I need you to know about etcd right this second is that that is a database that is storing all the configurations for the environment being supported by this solution in key value pairs. And really, you know, if I really had to break down what that means to me, let's say we had a field named called name, okay, and then name had a value of Peter Staarfaenger. That would be a key value pair. And so this database is just hosting that effectively. We also have something called the scheduler and the control manager. Scheduler's purpose is within the Kubernetes environment is that if you know, a developer or an administrator decides they want to build some kind of a container in the environment, we're going to build on really what that means, a resource. I'm going to say a resource for now. That request would go to the API server, and the API server would then go to the scheduler to determine what worker node, again, now we're out in the data plane, actually has enough resources to run the container that the developer is asking be built. So the scheduler's sole purpose is really dealing with capacity and deciding where things run. And then finally, we have the control manager. The control manager is really what's assuring, if you will, that you have uptime as far as any services that you're trying to deploy through Kubernetes. And so it spends a lot of its time collecting metrics and health indicators to assure that your services are running as expected. All these components parts, again, if we watch the arrows, they all go back to the API server. And that's really important when we start digging into forensics or incident response relative to this master node, which is also known as the control pane. Now we're going to move a little bit to the right. Now to the right, again, there's a little bit of new here. And to point at, again, what's not new is our container itself running. Again, we always have some kind of a runtime engine. Last time we talked about Docker. And the way that Kubernetes fits with this is that it adds a couple new components. One of those components is a kubelet, and the other component is kubeproxy. Okay? The kubelet's responsibility is to check back on the API server to see if there's anything that should be running on its particular server that it's running on. Effectively, it's just an agent. The kubeproxy's role is to check back on that API server and to make sure there isn't some kind of a network configuration it should be considering in order to allow communications to flow to, again, any of these containers we might be running out on our worker nodes. Now, I keep saying containers, but container is an atomic unit, if you will, to the Docker engine, or again, whatever the runtime containerization technology is. However, when we speak in terms of Kubernetes, they call them pods. And so our pods are effectively created by the kubelet talking to the underlying containerization runtime engine, and it gets those instructions by checking on the API server, and the kubeproxy assures that any of these pods that exist within our data pane are able to speak to each other by making adjustments on the firewall rules in the proxy settings, effectively, that are on the worker nodes themselves. Now, we could have thousands of worker nodes and thousands of containers running on those worker nodes. All of that is part of the magic, if you will, and we're going to get past the word magic. All that is part of the magic, though, of really, what the components on this master node are managing for you. Okay, and just a point, we're not going to dig into this because it's from our first presentation. We also have an image registry, and folks, that's really where the images that make up our containers that the developers might use to run their apps on top of it would live. And again, we covered that very heavily in our first presentation. Next slide, please. Here we go. So, and this is orchestration, right? And what we see on the screen, again, we're just going to work left to right, because that's how I know to read things. Again, we have somebody who's sitting at a computer working, and they're executing kubectl is an administrative utility for the Kubernetes environment. And so they're executing kubectl and usually do some verb-noun combination. And here we're pretending they're creating a deployment. Well, when you execute the kubectl command, you might point at a file that's on the system that contains something called a manifest. And so I'm just going to kind of point at this box here that's meant to represent a deployment manifest. And really what's inside of it is that it has some metadata that gives a specific name for a deployment that's going to be created inside the environment. And then it also creates a label called engines. And just remember that I mentioned there's something called labels with resources we create. And then there's a specification that says, hey, there must always be at least 3 replicas. And so what that says to the controller, remember that control manager, is it says there must be at least 3 running instances of whatever I tell you next at all times. And then there's something called a selector, and the selector says anything that has this key value pair, right, an app with the designation Nginx, this is applicable to it. So there should always be 3 instances of this. We can go a little bit further and we see another subsection called template. Please don't feel like you have to write anything down. I'm going to publicly release this and give you cheat sheets and all kinds of stuff and links to training. Now underneath the template, we say, well, what is inside these replicas? And so we see some container-esque language, some Docker file-esque language. And effectively, in the metadata, we say for the templates, hey, they're going to have this label, Nginx, okay? And then specifically, I want you to use, first off, name them Nginx, and then use this image, so Nginx 1.1.4.2, I hope I'm seeing that right, I think it's, 1.14.2. And what that means is, on the previous slide, we have the registry. So when this goes into the master node, it's going to call out to one of those worker nodes and say, hey, pull from that registry this exact version of image called Nginx and start running it. And then finally it says also allow access to port 80. And that's really important because what that says is that on this pod, that's going to get created with this deployment, we need to make sure that port 80 is accessible to the cluster network. Because the rule is, with Kubernetes, whenever we deploy pods, there's a standard that says all pods must be able to communicate with each other. So the kube proxy, when it sees that port 80 should be open, it's going to make adjustments to the firewall to assure that all pods can always talk to port 80 on this particular device. Now, again, I just talked through a whole file. What does it mean when we say orchestration, right? We kind of said it. So, we execute a command, we pass it this file that's going to create an Nginx deployment, and it goes to the API server, report 8443, and then the API server sees that there's a deployment. So it goes over to the deployment controller. Now, earlier we talked about the control manager. Okay, I'm going to start calling out some little pieces, parts, but they're all inside that control manager. It's one utility running in memory. That one utility in memory has all kinds of little subcomponents, different controllers that are dealing with all these things that we wrote inside of our manifest. And so, we'll have a communication deployment controller. Hey, there's a section here that talks about deployment. Okay. Ooh, folks, I thought we were going to lose power. And then next, the deployment controller sees there's a replica set. So the replica set controller gets contacted. Replica set controller sees that there's pods that are supposed to be created. And so that is told back to the API server. API server then checks in with the scheduler. Scheduler says, well, server B, again, or worker node P, has enough capacity for this. That's where you're going to run it, and it communicates that back to the API server. So now, sitting in the API server, all our kubelets are polling, right? There may be hundreds of servers, maybe there's just two like I drew in the picture. Well, they call back and they see, oh, the kubelet says, oh, I'm supposed to be running this pod. And so now it builds the pod by talking to whatever the container runtime engine is. Once that's in place, it communicates back and it says, okay, I've built it up and here are its network needs. Well, then the kube proxy calls back, it picks that up, and in this example, we're going to go with, I must have did this for a Linux host. The kube proxy would make adjustments to IP tables, and if you haven't heard of that, IP tables, again, it's just the firewall on a Linux host. And so we make adjustments to IP tables so the communications that were written in that original manifest do function. Now, from here ever forward, again, this API server will continue, because of queries from the controller, will continue to do checks on the kubelet to make sure that the replicas that were asked for are always running out in the environment. Everything I just described to you is this idea of orchestration, and that is what Kubernetes brings to the table for us. Next slide. Okay, so what are our deployment options? Again, there's a lot. So you could totally do this on-prem, kind of overkill, but with that being said, there's several utilities for it. There's kubeadm, that seems to be a way that a developer could potentially deploy a Kubernetes environment. There's kops, there's kubespray, and these are kind of some of your options if you were going to go production with your deployment. It was going to be on-prem. There's also SaaS offerings. I will cover this in my next talk from a forensic point of view. But you can deploy into GCP as an example. That's a Google Cloud platform owned by Google. There's AWS that's owned by the company Amazon. There's Azure that's owned by the company Microsoft. Shout out to my Microsoft folks on the line. And anywho, but there's so much, and so there's a group that is a derivative of, and hopefully I don't get this wrong, but from the Linux Foundation, it's the Cloud Native Computing Foundation, and they have a huge landscape slide that actually tells you everyone out there who's certified to offer Kubernetes as a SaaS. And so do check that out. Again, we'll have links for you later. And then for educational purposes, I wrote educational. That's not really fair. We should say development. So if you at home are going to write an app and you're trying to make sure that it'll run fine within Kubernetes, you might use one of these utilities to stand up an environment. I use these utilities very heavily for my research. And so there's Minikube, and a lot of what we look at today was actually built for Minikube. There's kind. All kind is, it's Kubernetes, but you're running it as a container. And again, kubeadm is pretty well documented, so it has great carryover if you were going to do development within Kubernetes. Next slide. All right, as far as Kubernetes security, again, what's cool about the people who work on Kubernetes, they have something called SIGs, and they're special interest groups. And so there's a whole special interest group that is just strictly dedicated to this topic of security. And all their talks, every one of their weekly meetings is right there in the Kubernetes YouTube. But that being said, when it comes to the API server, some options you have are things like authentication plugins, so you can enhance how authentication may happen into your API. There's also this idea of using config maps versus using another kind of resource called Kubernetes Secrets, which does start to introduce some encryption. And then of course, if we're going to use one of the major cloud providers, or you can do this on-prem at this point, you probably, for your secrets, you probably want to use some kind of a vaulting technology to protect your passwords and keys and things like that. Because when we get into the forensic side of it, what we end up learning is if we store this stuff in its natural state within Kubernetes, it's only base 64 encoded. Pretty much it's in clear text, right? So that's an issue when it comes to adversaries hitting our environment. Also RBAC. So RBAC exists, and really all that is role-based access, right? It's supported within this product, and again, if you choose to be an administrator one day of one of these environments, that can take advantage of it. And the big thing I want to point out here is that there's accounts for people, and then there's accounts for services. A lot of times, and this will also be not the next talk, but the talk after, you might integrate your CI/CD environment, which your continuous integration, continuous deployment, like maybe a code pipeline where it's able to deploy on your behalf into all your Kubernetes deployments. And so, anywho, we want to make sure it has a different account than an account that you might want one of your developers to use. And then when it comes to security and this says node security, what I meant to put here was worker node security. Again, we still have a lot of our mechanisms we learned from the containerization side, which is like network namespace, PID, IPC namespaces, in order to break up, again, how our containers are able to speak to each other. We could also set security context. That helps as well with security of the worker node itself relative to pods. We could also assure things like by not granting root file system access to our pods when it's not necessary for the functioning of our application, or removing things like privileged access to the underlying host. Those are all valid moves that we can take to not do when we write our manifest. There's also something newer called pod security policy, which seems to be pretty advanced. It has some monitoring modes, but effectively, the community that develops Kubernetes went out of their way to effectively take all those things that make pods insecure and just set it where effectively it's a yes, I want it turned on, or put it in monitoring mode, or no, it's turned off. But effectively, if you set it to yes, it's not yes. I know some of my Kubernetes folks are like, you're not saying it right. But effectively, you can set this pod security policy to yes, and now a lot of these concerns like, can someone run a pod in a privileged mode are not possible. And finally, we have something called network policy. Network policy is cool because earlier I mentioned labels, and from a label point of view, you could write firewall rules that say that anything labeled with Nginx should never speak to something labeled with database, as an example. Just have a police officer walking here. All right. And then finally, there's also this idea of pod proxies or service mesh. And at this point, we're starting to get into third-party integrations, and there's a lot of these third-party plugins and everything else that work with Kubernetes to give us security. But the idea is that the people who've been working with this for a while have figured out that you can instrument a lot of security by getting rid of some of the underpinning weaknesses by introducing a proxy container that effectively acts almost like a sidecar within that pod that would run in front of the container that's running your application. We'll show a little more of that later. Okay, next slide. All right, folks, we're finally the forensic part, right? All that preamble to get to the forensic part. So, the items in light blue, I'm not going to be covering this time because we had to pick something for hopefully keep that an hour. But effectively, we are going to take a look at what our forensic opportunities are on the master node from an SME point of view. We are going to look at controller, manager, API, server, scheduler. We're not going to talk about core DNS, but I'll just kind of mention what it is we might care about from a core DNS perspective. And we're also not going to take a look at risky manifests. Again, manifests are just your infrastructure as code. They're very similar to your Docker file that we talked about in the prior presentation. Again, it's just how we're defining our resources, right? Like our developers can define risk there. And then from a worker node point of view, definitely going to dig at that kubelet. We're going to look at the kube proxy. We are not going to talk about our forensic opportunities as far as the setup and administration tools are concerned, but I will point to a couple forensic artifacts very shortly. And then on the data plane side, when we look at the pods themselves, one of the things I discovered, and this was part of research and reading, was that whenever a pod is created, even though we might be writing a pod to run our application, actually what happens is there isn't just one container created, there's actually two containers created, okay? And that other container, I'm calling it a network endpoint container here. I think the folks who make the product call it an infrastructure container, but effectively that other container's job is to simply handle all the networking for all the other containers that might be inside of a pod. And so it too has value to us in case it's abused. And again, there's the app container, lots of opportunity there. And then of course, naturally, what do the pod logs look like? We talked about the Docker runtime environment. We hit very heavily on that. Containers are spitting out a lot of logs for the services that they are exposing. Okay, next slide. All right, so here we go. Just kind of getting into some of the forensic artifacts we might see. Again, on the master node, we're talking about that API server. In some environments, you'll find that a lot of logging is kept underneath kube-API server.log. And then, of course, the configuration, typically for all these components, are usually kept in YAML files. And so, again, anything with that kind of preamble kube config is very interesting to us. When it comes to core DNS, the one file we're kind of after, because core DNS is really kind of some of the heart and soul, if you will, of the functioning, of the cluster environment. Because what core DNS does is, a pod can live on any worker node, right? That's a principal thing. And so what that means is that, from an IP perspective, its IP could be anything, anytime. We really don't know the lifetime fully of a pod or any particular container in the environment. And so the way our developers are able to work in what I would call chaos is that core DNS brings to the table for our developers the ability to always reference a name. And so earlier in our deployment file, we named our containers Nginx. Well, what does that mean? There will always be an entry within core DNS for Nginx. So you could reference that from a code perspective. But the core file, what's inside of it is not only our, what DNS resolution should be done within the cluster, but also inside of it there's effectively conditionals on what you do when. And so, again, we're not looking at it today, but if you want to look at core DNS because it's relevant to your investigation, look for the core file, look to see what's inside of it. Maybe there's some hijinks. Again, that's what you'd be looking at there. Scheduler, again, scheduler has its own log, also configuration file, always want to look at that. All these configuration files usually point to where the secrets are that are being used by those different utility components to speak back to the API server. And so, to you as a forensicator, that gives you clues on potentially things that might have been stolen, especially if you're working a case where there might have been indicators that somebody had managed to get a foothold on your master node. Again, controller manager, more config files here. And then etcd, what I found that is fantastic there is there's something called write-ahead logs. And write-ahead logs are always just collecting all the changes that are happening in the environment. And then there's something called, it's actually SnapDB, or snapshot database, and that's actually that key value store. And so what we'll see here in just a minute is that everything that's stored there is actually just stored in ASCII, and that's an advantage. Next slide. All right, folks. So we're about to see some pictures. But for this slide, look, just showing the worker node. Again, worker node kubelet. Lots of great files to look at. We're going to look at those very up front and close here to see if there's anything we want to cover off on. Yeah, I'm just going to point here real quick to the kube proxy side of the worker node. The kube proxy is interesting because we are able to dump the IP tables on the system. Then effectively, it's easy to spot all the changes that have been made. With that being said, get a copy of memory. We'll see here in a minute. We can actually reconstruct all the changes kube proxies made on the system. As far as setup tools, lots of great places to find that. This will be available to the public soon. Next slide. All right, so here we go. Anybody know anything about this penguin? Anyone know the penguin's name? All right. Penguin's name is Tux. You Adam knew that. And so, anyways, Tux is the mascot for Linux, and so we did use a lot of open source tools for this, and it seems always appropriate to use Tux. And so we're going to use our naval compass to kind of glide around this Kubernetes environment and just talk about, what our forensic opportunities are. We are starting off with the API server. Next slide, please. So what you'll see here is where I was using a tool. It's Volatility Framework version 2. There's a new one, version 3. You should probably go check it out. But I preferred version 2 because it had some plugins that had a lot of meaning to me. And I use these pretty much on every component. So I'm just going to point to them this one time so it's easier for me to go through the next slides. So I ended up using the plugin Linux PS tree, and that really just allows me to kind of get a tree view on my processes. I also used another one, Linux PS AUX, and really what that does is it spits out the command line that's in use with whatever running process is in memory. We also ended up using PSENV. And what that does, it shows us the environmental variables. One of the things that's passed on to all these pods are environmental variables that lets the pod know how it can speak back into the environment around it. And so a lot of times our developers are heavily reliant on these environmental variables when they write their application. The other kind of truth there is that when it comes to all these utilities that are running on the master node together, right, to create that control plane, even the developers who created that need certain environmental variables set for their tools to run. And so when we look inside of here, what we actually end up seeing, again, what's on the screen is that I'm looking at, so we used a tool called Minikube in this example, and Minikube spun up a master node inside of a container. And so this very first entry is familiar to some of us in the sense that it actually shows what the container ID is. And that is great for forensics because anything that happens inside the container is written back to disk. And so we can always explore that later when we're trying to understand what happens over time with the software. Well, the next entry is the actual API server, and that utility has a really specific name. It's kube-API server. And then what's inside of the command line there is the actual network identity that it's going to assume. We actually have what level of privilege it's running at, and we can even see the locations of all the secrets and keys that it's dependent on in order to operate. And so as a forensicator, right, we want to remember those locations, because those could, those locations, again, depending on the context of your case, might be being abused. Then we also see from an environmental variable perspective, we kind of see, again, what the load library path is. Again, that might be useful to us in case there's some kind of hijinks going on as far as libraries that are loaded into memory. And we also see, again, more information about where specific certs are that are needed by the kube API server utility. Next slide. All right. And so here, what I did was I ran another plugin. This is Linux_netstat. And really what I'm looking at, when it comes to netstat shows you all the active network connections that are on the machine. When it comes to specifically TCP-based communications, all those have to be tracked by the operating system. And so if you think back earlier when I was talking through how communications flow into the Kubernetes environment, everything must go to the API server. And so our first opportunity, again, if we were working a case and we got a copy of memory from a master node, is to look and see what communications were actually coming into our service that is the API server. And what's on your screen right now, it's not anything that's alarming, but we can see that there's a listener on 8443, and then we see that there's communications going to port 2379. Those 2379 communications are actually just communications back to etcd. What I would be concerned about as an analyst, again, is if I had any unusual communications, foreign IPs that were connecting to 8443 that were outside of the networks that I would have authorized to speak to my API server. So that's really the opportunity here. Next slide. All right, and then the other kind of thing that I found was when I looked into memory and I just started checking what it is I could find within that memory space, I actually found that I could use keywords like, I could say registry and then say a particular resource I was looking for, like let's say I was looking for a pod, and right there in ASCII in clear text, I could see every pod that the API server knew about. And so listed on the left side of the screen are all the possible resources, or at least the ones I wrote on the slide, that you might create inside your Kubernetes environment. And so effectively what this taught me as an analyst is that I could query for each of the different resource types and iterate them out, and then use that iteration to find, did somebody introduce something into my environment from a master node perspective that might be malicious. The other kind of just game day highlights here, there's a lot of documentation how to interact with that API when it comes to the API server. And so I found a lot of the conventions that are documented on the Kubernetes documentation website work in memory as well. All of this is ASCII, and I just can't stress that enough. And so it's very easy to find. Next slide. All right. And then here I'm just showing, I took a stab at the container configuration, and really what I'm showing here is that on the screen, at the very bottom, you can see all these volume host folder references. The reason why that's important is whenever it comes to a volume host folder, we do this for our containers so we can expose maybe specific files to the container, right? That's the reason why you would have a host folder. What I didn't see was any real storage being referenced outside of the container, and I don't think I show it within the slide deck, but really there was just use of something called tempfs. And so really from a file system perspective, there wasn't much going on for me to discover from a forensic point of view. So lesson learned for me that I'm sharing with you is, if you had concern about your API server, you need to get a memory capture if you really want to investigate that further. And again, we're kind of jumping past the availability of logs, but if you can get memory, we can interrogate further to see if there is maybe a risk we need to be concerned with. Next. All right, and here's some of the logs, and we're not going to spend much time here at all, but here's the bottom line. Because this API server was running as a container, that meant that every interaction effectively was being logged naturally, and so this is just those logs on the screen. Next slide. All right, so we're going to move on to etcd. Again, etcd, I can't tell you how many developers have told me, Peter, you're going to do forensics on this stuff, and you're concerned about the control plane. You really need to understand etcd. And so if I had to say where the gold was, if there was anything worth looking at, like if we had concern about insider, or maybe it's an accidental insider because some credentials got hijacked from one of your developers, again, we're probably going to find that proof of abuse in etcd. Next slide. And so here we go, again, still running our same plugins. And really what I zeroed in on as far as the command line here is that in the arguments I could actually see where it says the data directory is, okay? And so that's something as an analyst I got hung up on, because etcd's role is, again, to store the configuration for the entire environment. Other kind of items here of value were, where is etcd listening? What other ports do we expect to be on etcd? Because from a host point of view, when we do look at what sockets are open on a server, again, I would expect for the host that had etcd to strictly only have the ports open for its functioning. So if we have anything extra running, again, we probably want to interrogate that. And then again, just pointing out, as far as the environmental variables, some of the communications, are being kept internal to the cluster, not going through a proxy. You can also see some FQDN and other things that might be interesting if we're trying to pair logs with, pair logs from our environment. That originally gave us concern to come, and look at this particular component. Next slide. All right. And so here I'm actually listing out all the open files. And what I ended up learning when I listed out all the open files that etcd had, I ended up finding, again, this snap database file, and I ended up finding this write-ahead log. Next slide. And then when we look at it from a network connection point of view, again, if we think back to our diagram, the only component that should be communicating to etcd is the API server. So if we know the IP address of our API server, but we come here and we find, again, IPs other than, that's probably a big hint to you that some third party might be doing hijinks with your actual backend database for this environment. So that's kind of a big deal. Everything else listed here, I'm just going to kind of point to it. This is really just etcd communicating back with the API server. Again, there's nothing exciting here because I'm not looking at a compromised box. But that's the value of this view. Next slide. All right. The other thing that I was tackling is, we talked about this idea of an image repo where all the images are being pulled from that create our containers. The containers go inside of pods. Pods is the smallest atomic unit of resource that you can manage with Kubernetes. Okay. And when I took a look at memory and I said, well, hey, on this machine, I had it all in one, right? I had my worker and master node all on one server. And so when I looked, I said, well, show me memory forensic tool, volatility, show me all the containers that are in memory, and I got this list. And I knew that I had certain containers in memory that were connected with a pod. And so then I said, well, etcd, show me what containers you know about. And what I ended up finding was, when I did a quick check against the write-ahead logs, and I don't have any grepping the SnapDB database, but when I just grepped just for that identifying string, boom, it was all being tracked. And it was being tracked to a point where I could see what image repo it came from, as well as what the current identifier was in memory. And the value of that is that, let's say we did have, the malicious insider, because that's a thing, and they decided to go out to an unknown registry. Well, hello, look at all the image registries that are being recorded right past that Docker pullable phrase. If we see a FQDN that we don't recognize, that's probably a clue. That's probably somebody who had bad intent. And then kind of the other side of it is, we also have, the name of the actual container engine, and then finally the identifier for the container. Again, that could be valuable to us in the context, because now from a Kubernetes point of view what the actual runtime pod looks like, especially if it's malicious. Next slide. So here we are, just taking a little bit more at etcd. And so one of the things I pull out is I say, hey, let's look at that command line one more time. And what we see in the command line is that there's an argument being passed that says, it says a lot of things, right? It talks about all the different components within that master node. Well, when I look at the actual etcd database, it actually recorded that entire configuration that should be in memory. And so to me, the opportunity here is that, one, I could verify the configuration that's in the database. Two, I could verify that configuration against what's running live in the environment, because it's right there in the etcd database. And in clear text, you and I can read this. That is amazing. It's not always that way. Usually, again, it's in formats that people can't just read easily like this. Next. All right, and so here's another example. So just building on this Docker pullable thing, let's say we found a container, we found an image that came from an unusual repository, and we were concerned about all the containers surrounding it. Well, when, let's say we don't have a live environment to query, what we can do with etcd is we can actually query, again, on that particular image we're concerned about. And if we just, when we search, if we just say, hey, back up 2 or 3 lines and show me what else is there, we get 2 valuable pieces of information. One is the actual IP address of the pod. The other thing we get is the actual IP address of the worker node. Okay? So if we did have some hijinks at the control plane, we can now track from the etcd database where in the environment the malicious stuff is running. And that might help with our containment strategy that we probably need to start thinking about here real soon for at this point. Next slide, please. All right, and so, again, in memory, we could definitely search and find valuable information. When it came to, the actual files themselves, we could still kind of use that same, the same kind of keywords. We start with the prefix of registry, and then we say what the resource type is that we're interested in. If we know the resource type and the namespace, I'm going to talk about namespaces. If we know that the namespace as an example, again, we can pair those things together to get down to, those resources that give us the greatest concern. Next slide, please. All right. And here, this is just me showing, look, if you're not using a secrets manager, this is me hitting that database. So imagine if an intruder gets onto your control pane, right? And they get to where etcd is. Well, now they would just go through your database, and this is just base 64. This is a base 64 encoded token. And so boom, they got your credentials, right? So if you find an attacker, wherever etcd is, they probably got all your credentials, and you can rotate all those secrets. Next slide. And look, and what I wanted to show here is everything I've shown so far is this weird command line. I guess this is also command line. But what's different about the other command line is that it was us going against raw data, right? And we're going out there and I'm like, it's asking, it's blah, 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 blah. But we could skip all that. If we get a copy of a disk or memory, let's say these files are resident in memory, and we're able to get those write-ahead logs in the database, we can actually restore that. And that's what's on the screen. And what that means to us as forensicators is that we can use a tool that's native to Etsy. It's etcd-ctl. And so we can run this etcd-ctl tool, tell it where our database is, and we can tell it where the write-ahead logs are, and we can say, go ahead and restore it. And then we can run it. Now, I put a fun slide in here, and really what I was pointing to was I was attempting to do this on an Ubuntu machine, and I installed whatever version of etcd they had in their repo when you do the apt-get install. And anyways, it turned out my version was wrong. But immediately in the error message, I got what version I should be running. And so I ran the right version, I pointed it at the database that I just restored. And next slide, please. And that last picture was it running. Now I'm able to run queries against it. And the way these queries look is, again, I'm using that same tool, that etcd-ctl. I run git, and then I use this forward slash, and forward slash says start at the very top of the data, and then I say show me all the prefixes, and show me only your keys. And then I specifically look for pods that were running inside the default namespace. And boom, here go 2 pods that I knew that I had ran in the environment. And so the power here is that we can use tools like the IT people while also achieving our forensic goals of preservation because we got the files from some forensic images we took, right? And again, here I just go a little bit further and I say, oh, this pod called balance gives me great concern. Okay, etcd cuddle, I literally write what the tool returned to me here, and here I'm piping it through more, and now I get all the information that etcd knows about that pod. Good stuff. Next. All right, so moving along, scheduler. Next slide. Again, scheduler's role is to figure out where should we run our resources. Is there enough hardware available? That kind of business. Really, what I zeroed on here was I kind of crunched everything in one. My concern was controller, where are your secrets, because it's able to give instructions to the API server, and that's why I care about it, right? And then also, I don't expect anything to be talking to the controller. The controller does listen on port 10259, but I would never expect any communications coming to the controller. There's no reason for it. So if you have foreign communications, that's a big deal. But what I do expect is it to speak back to our API server. So here we have it talking on 8443. That's perfectly normal. Knowing normal is how you find evil. Next slide. All right, this is me hitting those configuration files that were referenced in the command line. What's in there? Again, secrets and where to use them. And so here's the bottom line. If we have an adversary with a foothold, where this stuff is, check your configs, because these things are now at risk. They need to be rotated. Next slide. All right, as far as finding resources, now, I don't know what the dilemma would be where you wouldn't be able to get etcd, but you got the master node that was running the scheduler. But even in scheduler, you can find the resources that are on the machine. Again, using very similar conventions where you state the resource, state the namespace, that kind of business. There's other info here that I'm sure is useful, but when I went through it, there was a lot of things that were important to the controller. But as a forensic analyst, I couldn't find value beyond iterating resources and making sure there was nothing rogue in the environment. Next slide. All right, and here are the logs. Again, this was running as a container. We're not going to read logs here. Next slide. And then finally, controller manager. Again, controller manager's job is if we say that there should be 5 replicas in the environment, the controller manager is always going to reach back out to the API server, say, hey, API server, are those 3 replicas still running? And the API server is going to go, I don't know. And it's going to reach out to all those couplets and get a status and then report back to the controller, right? And figure out if we need to, spin something else up because there's a problem. Next slide. So when it comes to the actual controller itself, again, we find a lot of great pointers to configurations. We always want to look at those to know where our secrets are sitting at and where they potentially put at risk based on, again, context. We also find things like the CIDR range for the service cluster. That's really useful in the sense that we can have an idea from an IPing perspective where we would expect services to live within the cluster. Okay, next slide. All right. And again, here it is. We have a listener. That listener is meant for communications that are internal to the COOP controller. It's not meant for the public to access it. So if you did see communications coming in 10.257, again, it's probably an adversary. Communications out to 8443, totally normal, because it should be talking to the API server. Next slide, please. All right, and again, here I'm just digging at, I guess this was just another sanity check, folks. There's a lot of good stuff in here around the config, and all this was in the CLI, but I think what I kept trying to show here is just simply that when it comes to data, there isn't much of interest from a data perspective on disk. It's all in memory. There's a lot of good stuff here, but it's in the command line for the running utility. Next slide. Again, here's me just hitting those config files because I'm doubling down on these secrets are at risk. Next. Again, logs. Next. And then finally, resources. It seems like all the components, the one common theme was any resources in the environment. It seemed like no matter what utilities memory space I was looking at, I could always find what resources were in the environment. Hopefully this passes the test of time, and so I'll keep experimenting to see if there's any conditions where that's not true. Next. Finally, getting down to now the worker node, the data plane. Let's look at COOP proxy. Next slide. All right. One thing to know about COOP proxy, its sole role is, again, just to change those firewall rules. It's not doing any kind of routing. There's a component that I didn't touch on because we have limited time here, but there's a plugin called CNI, and that's actually what's handling something called an overlay network, which is really what's doing all this routing between all these worker nodes in our data plane, right? But again, the COOP proxy, the reason why we care is that if the firewall rules don't allow the communication, then it's not going to happen. And so, again, if it's in the firewall, then the comms could probably happen. That's why we care. And what it is, what we see within kube proxies, that kube proxy knows the destination of wherever core DNS is going to be for the environment, and it also has just really all the critical services being passed as an argument to the command line. And so if you were trying to draw a picture for yourself on how these administrators set up their environment, I feel like the kube proxy, if you find that on your worker node, you could probably write a pretty clear picture, which would then allow you to interpret data, look back and go, okay, do I have any unusual communications going back to this infrastructure? Next slide, please. Okay, so in here, I'm just, again, showing the communications that are going on. There are a number of listeners, and I know I'm going to say this badly. So kube proxy comes packaged with something called Prometheus, and Prometheus is really what allows the master node to be able to do all these health checks. I think Prometheus is also bundled with the kubelet. I think I'm getting all that right. So there are listeners, and I would expect communications coming to those listeners, but namely from the API server. Again, I would not expect foreign communication coming to any sockets that you see. As far as outbound communications, I would expect communications back to the API server, because whenever we spin up new pods on a particular worker node, again, the firewall rules have to be configured. So kube proxy polls, it goes, oh, something new was just created. What's the configuration? Okay, let me set up the firewall rules. Next. All right, and again, here, just taking a tackle there at the config. What I found was interesting, this particular config file that was referenced in the actual command line argument in memory is the location of another config file. So next slide. And then in this particular config file, it actually points to where the secrets are that are associated with this, as well as what namespaces and things like that should be running on the box. And so this service account, again, could be hijacked depending on, again, the risk event that you're dealing with. So if somebody does have a foothold at a host level, this is ultimate risk, which puts, your environment at risk. Next slide, please. Alrighty, and then on this slide, really what we're digging at is, I just took a look at the container logs themselves, just a different view. Not going to spend a ton of time here, but, again, this service is logged into. Next slide. Here I'm just showing that, if you're familiar, so if you go look at the man page for, the manual page for IP tables, it really shows in there like how you pass arguments to IP tables to write all these rules. And so for me, I was able to use that as my key words to go find what firewall rules had actually been written. And this is from memory. And so, again, with memory capture, I could figure out everything that was authorized from a firewall perspective to flow to whatever pods were on that server. Next slide. Here we're just kind of taking a closer look at a number of different views. One is looking at what's on the local Etsy host file. Again, the only thing I'm pointing out here is that there are items written in the local host file from a container perspective that were necessary for again, master node function. And then kind of outside of that, we also see that there's a lot of different interfaces set up. Really what I'm leaning to here is that when we query all the interfaces that have been set up, in order for these pods to work, they have to have a virtual network interface. And every pod gets one of these virtual network interfaces, and that plugs back into a bridge on that system, the underlying host, the worker node, which then allows communications back out onto the wire to occur. And so, here this is just, again, listing out all those possible interfaces. In practice, you should be able to map all these IP addresses back to pods that are on that box. And then finally, the only other thing here that's on the screen, I didn't cover this during my Docker container talk, when it comes to the Docker runtime engine, it has a file, it's local-kb.db, and the power of that file is that you can go in there and actually find all the IP assignments for that particular runtime environment. Next. All right, moving on to the kubelet. Next slide. All right, Tux. Tux is riding along with us. So when it comes to the kubelet itself, here's what was interesting to me. The kubelet itself is going to get an argument on how it bootstraps the server, and what I could best figure out from that is how you join your worker node to be managed by the master node. And so it points to a really specific file that describes how it should be configured. We also see in the command line, whenever you run a kubelet, again, it's just running as a little software agent or a service, you also specify what the container runtime is. And that's valuable to us as forensicators because now, again, I have some public work on how you handle Docker, but what if it was Rocket, right? We may have to go do some homework if that said Rocket instead on how it is we forensicate those containers. We also see, again, the host name, that's not so great. And again, we can see at what interval it's checking back to the API server. And then finally, what is the node IP? And as far as environmental variables, I guess there's not many call-outs here. Next slide, please. And so, here's what it looks like from a network point of view. Again, you have that listener, that API that our API server should be able to reach back to on the kubelet. It's a limited API. Again, if you have wide open firewall rules, if you see anything but the API server speaking to your kubelet, that should be a concern. And as far as the kubelet speaking outbound, it should only talk back to the API server that you know about. Next slide. All right, and then when it comes, again, to the kubelet on disk, there's a lot of interesting stuff here. The bottom line is when it comes to secrets, the secrets are always mounted to this particular file, but it's done through a temp file system. And so from a pod point of view, I would have to explore this further. I couldn't really find how you put the secret at risk given that it's shared that way directly to the pod. But when it comes to some of the environmental variables for the kubelet itself, there's another file that's kube-adm-flags.env. And inside that file, once you find it on your worker node, what it does reveal is that it reveals, one, this one shows CNI, but in order for Kubernetes to function, you have to have a network plugin. And so one of the things we're not covering today are all the different network plugins that allow the cluster to function as expected. And so that's a forensic opportunity. However, the bottom line here is that if there is a special network plugin being used, you'll probably find it inside this file. The other thing that I found that was useful is the actual image that's being used for that network endpoint container that I was talking about, that infrastructure container that actually allows the IPing to work inside of the pods. Just one more comment there on that particular container, this container. When it runs in memory, it actually has in the command line pause, but what's underneath the sheet, again, is the actual virtual network adapter that I was talking about. And on all of the other containers running inside that pod, they reference almost like a bridge back to that one infrastructure container. And so the way that we end up creating resiliency is that we might have those back-end containers crashing and there might be problems with them, but our infrastructure container is always up and that IP is always accessible from that one container. From a security point of view and a forensic point of view, it is possible that this container, PAWS 3.6, this infrastructure container, could have vulnerabilities too. So I think that's worth paying attention to. Right now, there's nothing in the public, but you want to talk about the first point of entry to if you are able to reach the pod, it's going to be this container from a network point of view. And then finally, the kubelet is running as a service, so it is worth, someone want to let Brian Reynolds in. It is running as a server service, as a daemon service, and again, we can go look and see if there's been any monkey business on the disk itself. Next slide, please. All right, now we're going to take a look at the pods themselves. Next slide. All right, as far as the pods are concerned, here I was just digging, at an example, and really, what's special here. When I took a look at the memory space, for these pods, what I ended up finding was that we could search for the pods, the containers by their identity. So let's say there was a particular container that was giving us concern, and close to it would be the actual pod identifier. And so from a mapping perspective, it is possible that as an incident responder, you may start with a machine where you're like, this thing in memory, it's bad. Oh, it's a container. Well, what's the container ID? Okay, I got the container ID. Well, you search memory for the container ID. Oh, that's actually associated with a pod. That's a new concern, right? Because now we have to ask ourselves, well, how did this container that was acting badly get there, right? Was that container supposed to be there? Meaning it was just running vulnerable code? Did somebody introduce maybe a sidecar container because now they have access to our master node? The point is you can find the pod it's in, and we got to go back to our rule that inside a pod you can have multiple other containers running. What I would expect to find if it's a good pod is that it should be, again, inside your etcd database, and it should have, again, that pause container and then some other container that you recognize. If that's the condition and there's a bad network communication, that probably means there's a vulnerability in that pod. We don't know what that vulnerability is yet, but I think it's a big clue. All right, next slide, please. All right, and then here, is this really the next slide? Oh. So here I'm just showing that finding all the containers inside a problematic pod. And I'm just doing a query now, for what it is we saw on the last screen, and then just showing the output from it. Here's the bottom line. Whenever we have these containers in memory, if we find one bad container, we track it back to a pod. We get all the container IDs for all the other pods that are inside those containers. We definitely want to lay those out from a memory point of view and just see what else it is we're dealing with, and probably also from a disk point of view. And so that's really what I'm showing here. Pod equals many containers. Let's go find them all, and let's interrogate them with memory forensics and potentially disk forensics. Next slide. All right, and so here just kind of showing if I had IOCs from memory, now on disk I can quickly query for the IOC that I had from memory, this particular identifier that I had for the pod, you get results. Now, if I didn't have any memory IOCs, I could still go out there and find pods and what containers they're connected to, because underneath folder, it's data lib kubelet, all those pods are being tracked, and there's pointers there that point back to all the containers on the disk. Next slide, please. All right, so we're gonna do a little bit of warfare, right? We got our good naval tux. He's the helmsman. By the way, Kubernetes stands for helmsman. It's Greek, apparently. And then we got our evil hacker tux, right? They're going to war over the master node and the worker node. But what is it they might fight over? Next slide. And so this is according to OWASP. OWASP just kind of publicly shares concerns you might have from a worker node perspective is, hey, if you ever see a shell running inside a container, it's kind of unusual. A shell is like if we pulled up like an interactive screen. There's no reason for that if you're running like an application where you're providing some valuable service. Container mounts a sensitive path from the host. Just kind of being real here, if you see /proc being mounted or the root file system being mounted, that's probably something worth digging into a little bit further. Sensitive file all of a sudden being read. Here it shows Etsy shadow. I guess that's pretty low hanging fruit. But the bottom line is, right, there's going to be stuff where you're like, oh yeah, our developer meant to do that. And there's going to be other stuff where you're like, why is this credit card file being accessed by my logging application or something, right? And then finally, outbound network connections. It is possible that what led you there was you probably had a hit on some known bad, network IP address, and then you look and, oh wait, it's inside one of my containers. Now you got something to work on. As far as the master node is concerned, we're really concerned about process activity, how those communications are going on between containerized services. I spent a lot of time up here laying out like rules, right, from a network perspective. It all goes to the API server. Everybody talks to the API server. Nobody talks to anyone else. That's really important, right? When we think about network communications among all these different components. And then finally, network communications between containerized services and external clients and servers. When it comes to the Kubernetes environment, there's a very limited number of ways that we can expose services to the public, where like you or I could like just connect from a network. One of those is over something called a node IP, and that's where we literally say, hey, on that worker node, I want you to connect a socket on the worker node to a socket inside one of my containers. Okay, I would expect that to see something like that maybe in an on-prem deployment. Maybe that's where it would work because you didn't have a way to build a load balancer config. But if you saw that, like, let's say in one of those major cloud providers we shared earlier, that's kind of a red flag. Generally speaking, when we use these cloud providers, if we're going to create a service, that would be created with a load balancer, and usually that's a cloud load balancer, and there's other stuff. So if you ever saw on your worker node that there was, again, this connection between a socket on that host back to one of your containers, that might be a red flag. Other kind of indicators, of potential red flags could be things like the container now starts making, API calls where it's iterating everything in the environment, And so we definitely, almost want to take a look, at those web calls and just make sure that the APIs calls coming in are API calls that we would expect. Next. And so here we are, the hacker combat. So we're going to look specifically at the master node. So what if, right? What if one of these conditions happens? Next slide. So from my point of view, to me, right out of the gate, especially, let's say we had a virtualized master node, or maybe you're running at one of these cloud providers, right? You're running some kind of a compute resource. Get in there. Go ahead and, maybe it's virtualized. Snap that machine. Go ahead and get your memory, get your disk. If we can get memory and disk, you're onto the trail to be able to start to tell the story like we have through these slides. A lot of reasons why you want to do that is, logs are great, but logs can only tell you so much. What I just showed you, the logs will tell you some of that story, but it won't tell you the whole story like the stories we could tell with what we just saw. And of course, collect those audit logs, right? If we are in an environment that is mature enough where they have an external log source to put all their logs at, go ahead and pick those up as part of your collection, okay? And now we start to get into the examination. And so from an examination point of view, always want to start off that memory capture. I feel like that's the lowest hanging fruit in all circumstances. And we just want to triage for malware, right? And really what we're looking for there is, right, did we have processes in memory that might have a network communication that led us there? Is there, again, just something that doesn't look like a container or a component of Kubernetes running. And then finally, we do want to take a look at those system components, right? We want to kind of re-verify that, again, any of the libraries that are loaded with our system components, any of the handles that are open, this could be like a pointer to like a file on disk. We just want to make sure those are matching up appropriately. And again, checking those network connections, environmental variables, open files. We're looking at the configurations. The bottom line is everything that you've seen earlier in the slide deck, I show how to do that from a Linux point of view using Volatility version 2. You definitely want to go through those steps and just make sure everything kind of pairs up with what you would expect for your environment. And then finally, the image itself, right? We always want to mount the disk image of the host, and now we want to check for malicious modification of the startup of all those utilities that make up the actual master node. We want to verify the configuration of all the component configs. Again, kind of do that differential audit, right? Is what's in my etcd matching what's in memory, and then also running timelining tools, right? Typically, when we get alerted to bad things happening in our environment, usually we have a specific time that happened, and so if we start with that time and we compare it to all the system activity that we might see in disk or memory, because these machines are all little time capsules, we can usually find the story that happened before and after, right? We have time reference. And then finally, checking, those audit logs for unwanted user behavior. Usually, again, let's say we had a condition where the API server was being used in an unusual way. There's probably some definition of what unusual meant to us that moment. Go find that first, and then look around it. Next. All right, then finally, a little more hacker combat between the two tuxes. So we're fighting over that worker node. Next slide, please. Here, a little different. Really what we're after is we're probably going to come into the situation with some reason why we showed up today. I was mentioning earlier that really the only way to interact with these containers, if you're not part of that, that clustered environment, right? There has to be a service that's exposed, and so it's either exposed through a node IP or through a load balancer. And so, the first thing I want to do is if I'm alerted by the team, hey, there's something funny going on, I'm going to ask, well, what was the network communication originally? And now we have to go through the steps to figure out, well, what was the service configured for? When a service is set up as a resource, we can use our searches earlier, right, to go find the service definition. And that service definition is usually going to point to an endpoint IP address, and it's probably going to point to a node that's actually hosting that endpoint IP address. The endpoint IP address is our actual containers. That's now our target for further examination. And when we find that, right, now step 2 is a little shaky, right? So we can use, earlier we talked about network policies. We can write network policies where we now go label all those containers we're concerned about. We can say compromise, compromise, compromise. And then activate a network policy that says, if your label is compromised, you don't get to talk on the network, right? And then we can use another feature called taint, where we say, okay, now on this worker node where all these bad containers were running, nothing else should run there anymore, right? That's the feature of taint. Now, some red flags here. If you do this and you got the wrong crew in your house, you are blowing your cover the minute you take this step. So make sure you really have a strong handle on all the footholds the adversary might have. You may need to skip step 2 depending on how much you trust your logging and ability to interpret those logs and learn it. And then finally, right, we want to do bitstream copies on memory disk. Let's see there. We're going to do bitstream copies on memory disk, and again, review those just like we did for the master node. And then also this mapping exercise, right? We're going to go through this mapping exercise where we pair the pods with containers, because here's the value. Again, when we talked about container forensics, one of the things we pointed to is if you have a running container on disk that isn't connected to an image on disk, it's probably evil. If you have a worker node that is running containers that aren't part of a pod, they're probably evil. Go look at them. If you have, again, images that came from registries, image registries you're not familiar with, they're probably evil. But we need to go through this mapping exercise. We also want to check the configs. Now this is all container forensics, really. So we're going to stay on the slide for one more second. We're going to look at that container configuration. We're going to check its union file system, right? We're going to check all that to see what else it is that is went on to help us tell the story on what that container's purpose was and what it was able to achieve. We're going to leave it at that. Next slide, please. All right. So what did I do to really kind of build my baseline? So just a shout out here, Kubernetes in action. Spent a lot of time with this book. There's a lot of practical exercises, definitely. Give it a look. I felt like this gave me wings to get to the good part, which was all this analysis on the components. Also, I found there's this tech world with Nana. She apparently has a lot of stuff out there. But what I gravitated to was, in addition to the Kubernetes documentation websites, she had something called Kubernetes in 1 hour. And so I just kept doing that over and over with all the different deployment options just to kind of feel what that was like and then see how it looked from an analysis point of view. And again, the Kubernetes documentation website, if you can think of a question, you don't know what a resource does, you're trying to understand it conceptually, they did a really fantastic job. This community is amazing. Next slide. And again, I'm going to share this publicly, so I don't feel like you have to write anything down. But the tools that I used predominantly for this work was the sleuth kit. Again, I mentioned volatility, version 2. And also I used the Docker forensic kit. There's some videos of me doing that. If you look at the one of the presentations on the Columbus ISSA website, you can actually see my container talk and see me using this in action. But that gave me a lot of power in this particular example, because when I containerize all those services, I was able to easily track what changes they were making disk side, and of course easily spot it in memory because of volatility. Next. Again, special thanks to everybody. Oh no, the name is covered up, but Mr. Shaw over at Microsoft, I appreciate your help. Mr. Shaw is about to publish something from a log point of view on forensics, so definitely going to have to share that with the community. Also, Eldon Myers, Eldon is not here. I thought he was going to make a special flight in, that's why I looked around the room. He's watching us online. But anywho, Eldon really side chaired when I was making a lot of artifacts and just kind of doing some sanity checks, so thank you so much for that. Also, our favorite, Chris Lamberson. I'm going to go see Chris out at DC 706. We're going to present this there and get even more technical if we get more technical. But thank you to him and folks over there at Amazon. And also Casey Erdman. Again, Casey, just kind of a security researcher all-star. He really gave me a lot of feedback on this slide deck. And I think I'm going to have one next slide. Let me just make sure nothing. Okay. Future talks, I'm thinking, again, my next one's probably going to be on the SaaS version of this, so we'll look at some of the major cloud providers and what our forensic opportunities are there. What's different on the SaaS level is for some of the major cloud providers, you can't access your master node in some circumstances. So what do you do then? So I'm going to try to cover off on that. And then also CI/CD, when it comes to containerization, at the end of the day, right, we're writing code like we knew it, right? We're also writing infrastructure as code, right? That's those manifests and Docker files and everything else we've learned about. But all of that, in a production enterprise environment, that's all ran through a lot of other infrastructure. So what is that other infrastructure? What are our forensic opportunities if that gets hijacked? I'm going to point back to the SolarWinds incident, right? How do we find the SolarWinds events? We're going to get to that. Okay, we're going to pause right here. Does anyone have any questions about this presentation? Anything online?